Today we are going to be talking about ionic bonding. We, up until this point, have looked at the structure of atoms and how the nucleus is organized, and in particular how electrons are organized. And now that we have an understanding of how electrons are organized in atoms and ions, we can look at what does this mean for when atoms get together, when they form compounds or molecules. We're going to start with ionic bonding because in some ways ionic bonding at this level is a little simpler or has somewhat fewer features than covalent bonding. This isn't strictly true, but for our level, that's where we're going to take it. So we understand ionic bonding as the sharing, the giving and taking of electrons. This is something hopefully that you've had kind of an awareness of for a while now. And basically what happens is an ionic compound is made up of a metal and a non-metal, or a metal and a polyatomic ion. But basically we have metals that give up electrons. And now we've seen with ionization energies, for example, right, that it's relatively easy to remove electrons from metals and very difficult to remove electrons from nonmetals. And conversely, adding electrons to nonmetals is a more energetically favorable process than adding electrons to metals. So, for example, if we just look at the three general types of bonding that we are going to discuss, we've got ionic bonding. So, for example, table salt, sodium chloride, which is like the archetype of ionic compounds, where in an ionic compound, we don't really have molecules. There's no such thing as a molecule of sodium chloride. In sodium chloride, what do we see? We see the purple spheres, those are sodium ions, and the green ones are chloride ions. Now, each sodium ion is surrounded by oppositely charged ions, and each chloride ion is also surrounded by oppositely charged ions. So you can't look at one sodium ion and say, this sodium ion is ionically bonded to this one chloride ion. It doesn't work that way. In contrast, covalent bonds are a sharing of electrons, and each atom is sharing with one or more other atom specifically. So if we take the case of water, what do we see? We see high H2O, but we see each oxygen atom is bonded, sharing electrons with two different hydrogen atoms, and only those two. So, for example, if you were to melt and then vaporize sodium chloride, what happens is the sodium ions would separate from the chloride ions. You don't have a compound. This is a bit like what happens in aqueous solution. Water molecules and all covalent compounds, if you vaporize them, you have steam, they stay together, just like when other things dissolve in water, like say sugar, those things stay together. So we're going to spend a lot of time actually on covalent compounds most of the rest of the semester. The last sort of one we're going to look at is metallic bonding, and we're going to spend about a minute and a half on it now, and that's it. Because for us at our level, it's relatively simple. So metallic bonding, the model that we use is called the sea of electrons. Basically, this is a piece of sodium metal in the picture at the bottom. And you can see all in purple, all the sodium nuclei, so the Na plus, basically, and all of their valence electrons are just shared. They're like a giant ocean of electrons that is free to kind of whoosh around in the solid. And this is what gives metals their good conductivity. But that's it. That's all you need to know about metallic compounds and metallic bonding. It's just that. It's this idea that all the valence electrons are pooled into a sea of electrons. So, how do we represent compounds in our discussions of chemistry? So how do we just represent compounds basically on paper or on my screen? So the formality that we use is the Lewis dot structure. Some of you may have seen this, some maybe not. And the Lewis dot structure basically represents an atom or an ion with the symbol from the periodic table, and then however many valence electrons are present. If it's an ion, you put square brackets and the charge, and that's it. So remember, the key is when it comes to chemistry, when it comes to bonding, we only care about valence electrons. That's it. So for example, if you look at the structure of oxygen, the electronic structure rather of oxygen, it's 1s2, 2s2, 2p4. So there are 6 valence electrons in oxygen. And so how do we represent it? Like this. Now the question is, how did we arrive there? Now, if you recall, this comes from the orbital diagram, or the orbital box diagram, if you will, of oxygen. If we look at oxygen, so we said it's 1s2, 2s2, 2p4. And so if we were to do this as an orbital diagram, or an orbital box diagram, so we have the 1s, 2s, and 2p. Now, so this means we have 1s2, 2s2, and then we use Hund's rule, right, to fill the 2p. So 1, 2, 3, 4. And here we see we have in the valence, so we're really, again, only concerned about these guys here. So we have 2 paired electrons and 2 unpaired electrons. And this works really well for things like oxygen and chlorine or fluorine. Doesn't always work so well for things like nitrogen and a carbon. We're going to talk about why that is. So the formality that we use is you draw the symbol for the element. So in this case, we're dealing with oxygen. Right, so I draw the symbol O for oxygen. And then I start, it doesn't matter where I start. I can start at the top, I can start at the bottom, it doesn't matter. Then I'll have 1 electron and I go around in a circle. So I'm just going to go 1, 2, 3, 4, 5, 6. That's it. So that's the Lewis dot diagram for oxygen. That's it. If I wanted to do carbon, carbon is 1s2, 2s2, 2p2. So that gives me 4 valence electrons, right? So I do carbon, 1, 2, 3, 4. Now, you might be thinking, and if you are, it's right. You'd say, well, hang on, carbon, based in the orbital diagram, only has 2 unpaired electrons, not 4 unpaired electrons. The ones in the 2s are paired, and then these 2 are unpaired. The thing is that when it comes to bonding, and especially non-metals like carbon, where it's mostly covalent bonding, there's a whole bunch of other weird stuff that happens that we are going to talk about a little bit later on. And in fact, this model with the 4 unpaired electrons is more representative of how carbon actually bonds. And we are going to talk about why that is. So if we look at the second period on the periodic table, as we go across the periodic table, we just add electrons as we go, right? So lithium has 1 valence electron, beryllium has 2, and so on. That's it. It's as simple as that. Now, we'll get to that in a second. When it comes to ions, it's a little bit different, but not that much. Really, all it means is that you need to take into account the extra electron. So, for example, instead of looking at oxygen, let's look at oxide, O2 minus. So to go from oxygen to oxide, what happens? The atom accepts 2 electrons. Okay? We're going to add 2 electrons. And so what does that mean? How do we handle this? Well, really simple. Just like in electronic structure or electron configuration or orbital box diagrams, we just add more electrons. Same thing for Lewis diagrams. So if I have oxygen, which has 6 valence electrons, so 1, 2, 3, 4, 5, 6, I'm going to add 2 more. right? 7, 8. That's it. So it has 8 valence electrons. Then I am going to put square brackets like this around the ion and put the charge on the outside. That's it. So this is oxide ion. For cations, it's even easier. We took, say, sodium. So sodium metal rather, becomes, right, sodium ion, and we remove 1 electron. That's it. So sodium metal looks like this. Sodium is a group 1 metal, so it has 1 valence electron. So how do I draw sodium ion? I remove an electron, or the electron, and that's it. So sodium metal has no valence electrons. So I draw it like this, and I put square brackets around it, and I add a +1. So that becomes sodium metal. That's it. That's really all there is to the Lewis diagrams of ions. The next question then is, how do we talk about ionic bonding? We're going to spend a lot of time on Lewis diagrams for covalent compounds in a few lectures, but not yet. So since we aren't talking specifically about bonds between individual atoms or ions when we're talking about ionic compounds, what we're actually going to discuss, rather than ionic bonding or the strength of an ionic bond, is something called the lattice energy. Now, the term lattice means essentially a regular repeating pattern, and ionic compounds are organized into lattices, like a regular repeating pattern. So if you look here at our sodium chloride in the solid state, the ions are placed in a regular repeating pattern. Now, the energy holding all of that together is referred to as the lattice energy. And the lattice energy then is the amount of energy released when gas phase ions condense into the solid state. You could also see it the other way, saying it's the amount of energy you would have to add in order to bust apart those ions and get them into the gas phase. This whole gas phase thing matters a lot, because when we're trying to figure out what's going on, you'll recall that all of the values, the measurements that we have for things like ionization energy and electron affinity, those are all for gas phase particles. Okay. So what are the factors that affect lattice energy? Guess what? It's our old friend, Coulomb's law. So the two factors that affect lattice energy are the magnitude of the charges and the distance between the nuclei. Basically, how strong is the attraction between the charges based on how big those charges are and how far apart they are. That's really it. So some examples. If we look at something like, say, ion size. So that's the first factor we're going to look at. So here we have a series of group 1 metal halides. We have lithium chloride, sodium chloride, potassium chloride, cesium chloride. So now the product of the charges, right, the Q1, Q2, and it's the same for all of these. It's -1. It doesn't matter if it's negative or it's absolute value. It doesn't. So the difference is how far apart are the nuclei? What is the internuclear distance? And here we can see that as the internuclear distance increases, the strength of that attraction decreases. The lattice energy decreases. So we go from lithium chloride, which has an internuclear distance of 241 picometers, and it has a lattice energy of -834 kilojoules per mole. We go down to cesium chloride, we have an internuclear distance of 348 picometers and a lattice energy of 657 kilojoules per mole. So it's significantly less energy holding those particles together. Now, here's the thing that is important for you guys to recognize. You aren't going to have to know things like these values. What you are going to have to be able to do is do like ranking, like I asked you to do for things like ionization energy or atomic radius. You're going to have to be able to say, if I give you a few compounds, you're going to have to be able to organize them in terms of, say, which one has the highest lattice energy, or which one has the lowest lattice energy. Now, the physical manifestation that we can easily test in terms of lattice energy, because we can't measure lattice energy directly. We're going to spend some time a little later talking about how we get around that. But one of the ways that we can gauge lattice energy is by melting points. All right. So melting point for ionic compounds is directly correlated to the lattice energy. So compounds with a very exothermic lattice energy have very high melting points. Basically, the stronger the energy holding those ions together, the more heat you have to add in order to split them apart. Should make sense. So that's one factor, internuclear distance. The other factor is the product of the charges. And this, in general, is the more significant factor. So for example, here we have sodium fluoride and calcium oxide. Now, these two compounds have roughly the same internuclear distance. 9 picometers, not a lot, even on that scale. But for sodium fluoride, the product of the charges is -1. For calcium oxide, the product of the charges is -4. We can see that the lattice energy of calcium oxide is roughly 4 times greater. Not quite, but roughly 4 times greater than the lattice energy of sodium fluoride. So the product of the charges is higher, and so the lattice energy is higher. So we would expect, again, that calcium oxide would have a significantly higher melting point than sodium fluoride. Now, it's not a linear correlation. It doesn't mean that the melting point is going to be 4 times higher. I don't actually know what the melting points are. That's not important, at least not for us at this stage. What is important is recognizing that the more exothermic the lattice energy, the higher the melting point is going to be. The stronger the attraction between those ions, so that more tightly they're going to be held to each other. How do we go about measuring this directly? Lattice energy isn't actually a quantity that we can measure directly, unfortunately. So there is somewhat of a complicated cycle that we use in order to cope with this. All right, there's kind of a construct because we can measure lots of things, ionization energies, electron affinities, all kinds of stuff. But what we can't do often is measure lattice energy directly. So there's a process known as a Born-Haber cycle that we can do that allows us to figure out basically what the lattice energy is. So you remember that the lattice energy is basically the amount of energy involved when gas phase ions condense into the solid state. So if we can figure out the process involved in getting reactants basically into the gas phase as ions, and if we can know all the numbers related to that, which it turns out we can usually, then guess what? We can then say, well, the lattice energy is the thing that's missing. So I'll explain it to you. So let's take, for example, the reaction that we've been looking at so far, which is the reaction of sodium and chlorine to form sodium chloride. So the first thing that we're going to look at is the overall reaction. How does sodium chloride form? Well, sodium chloride is formed by this reaction. Solid sodium reacts with chlorine gas, form sodium chloride solid. Now, this isn't a balanced equation. If we had to balance the equation, we would say, well, there's 2 chlorines and 1. So we would put a 2 here and then a 2 here. And now we have a balanced equation. The thing is we want to try to look at what is the energy holding together 1 mole of sodium chloride ions? Right? Remember, the balanced equation is true for 2 ions or 2 atoms or 2 moles. It scales. So the way we can rewrite this equation to get a 1 here, and we're going to say solid sodium plus 1/2 Cl2 gives sodium chloride solid. Now you're going to say, wait, I can't have fractions in a balanced equation. And you're right, you can't, except when you're doing energy calculations. So energy calculations, the energy part of chemistry is known as thermodynamics, basically the movement of heat. And when it comes to thermodynamic calculations, you are in fact allowed to use fractions. So, but it's the key thing is it's only for thermodynamic calculations. So we're going to start with this reaction here. And the energy associated with this reaction, all right, is the delta H of formation, or the enthalpy of formation. Right? And this reaction here, we can actually measure the enthalpy of formation directly. You may have done this in high school, where you do a reaction in a calorimeter, sometimes it's coffee cups and a thermometer, right? And you measure how much heat is involved, and you do the Q equals MC delta T type calculations, and you can figure out the enthalpy of formation for a reaction. So that's great. Now, what a Born-Haber cycle tells us or allows us to imagine is, so here we have the reactants going to the products. That's the direct route. That amount of energy is the enthalpy of formation, the difference in energy from where you start and where you end up. Now, we want to know the lattice energy. Just from here to here, we can't figure out anything about the lattice energy. But we can imagine the process of going from the reactants to gas phase ions, and then from gas phase ions into the solid. And so we break it down into this process that we call the Born-Haber cycle. So the question becomes, how do I get to gas phase? Well, let's think about this. The first thing is I'm going to start with solid sodium. I need to get it into the gas phase, and I need to get it to an ion. Well, going from a solid to a gas, that's a process known as sublimation. And guess what? Heats of sublimation or boiling or vaporization, all of these are known quantities. They've been measured. So going from solid sodium to sodium gas, that is the enthalpy of sublimation. I've got it indicated here as delta H of sublimation. And this should come as no surprise to you, is an endothermic process, right? I have to add energy in order to get something to boil or vaporize. So that works really well. Now, there's a few ways you can organize your work in a Born-Haber cycle. Ultimately, it doesn't matter. I'm going to tell you my preference. You can do sort of as you see fit. My preference is to get everything to gas phase atoms, then move electrons around, and then do the lattice energy. Some people prefer to follow each individual particle or reactant separately. But I'm going to go with my method. So the next thing we have to do is look at getting chlorine atoms. Now, chlorine is one of the diatomic elements, and that means Cl2 has 2 chlorine atoms held together by a covalent bond. We don't know a lot about covalent bonds yet, and we're going to talk about them more later, but what we do know is that if we want to get a chlorine atom, we've got to break apart the chlorine bond. And that is the bond dissociation energy, BE. I've got it marked here. And what we need is, we only need one of the CLs. So it's a half Cl2 becomes one Cl. And so we only actually need half of the bond dissociation energy mathematically. Breaking chemical bonds is also endothermic. So you can see that now I've got gas phase atoms. That's pretty good. I'm part of the way there. The next step is to move my electrons around so I can get gas phase ions. So how do I make sodium ion? I remove an electron, right? Sodium gas goes to sodium plus and an electron. That is the first ionization energy of sodium, also a known quantity, also endothermic. Remember, ionization energies are always endothermic, no matter what. Now that the electron has been removed from sodium, where does it go? It goes to the chlorine atom to make chloride. So I have Cl plus an electron gives Cl minus. That is the first electron affinity of chlorine. And I've got it marked here as EA1. Remember that for most nonmetals, first electron affinity is exothermic. And now I've got chlorine to chloride. And now I've got my gas phase ions condensing to the solid state, and that's the lattice energy, and that is also exothermic. Now, in high school, you may have touched on Hess's law. And the important thing in Hess's law is that we can take elementary steps, simple reaction steps, and combine them almost like combining mathematical equations to give an overall transformation. And that's really the basis of the Born-Haber cycle. The key thing that goes along with that is that not only do the steps add up, but the energies, it turns out, also add up. So that works really well. And if you look here, my things cancel each other out. For example, here I have sodium solid. That's nowhere else. Sodium gas, I have sodium gas here, but I also have sodium gas here, so I cancel that out, right? I have chlorine gas here, chlorine gas here, so that also cancels out. My electron cancels out. Then I have sodium ion here and sodium ion here. Remember, they have to be on opposite sides of the equation in order to cancel each other out. And then chloride ion and chloride ions. And so what do I have left? I have sodium plus a half Cl2 gives sodium chloride. So because all of these steps add up to the overall step, what does that mean? Each of these energy values adds up to the enthalpy of formation. So the delta H of formation is equal to all the steps added together. Now, it's important in the Born-Haber cycle to realize that the general process is the same for all ionic compounds. The specific steps might be different. And that's because sometimes we're going to have an ion that forms a +2 ion, right? So for example, instead of sodium chloride, we're doing magnesium chloride. And so I'd have to do, I want to make Mg2+, but we have to treat those ionizations in sequence. So I do the first ionization and the second ionization. Also, it's possible that instead of having a nonmetal that's a gas, I might have bromine, which is a liquid at room temperature. So it's not sublimation. I might have to add in, say, the vaporization of bromine. Or if it was iodine, which is a solid at room temperature, I might have to add in the sublimation of iodine. So the general trend is the thing you need to pay attention to, which is get all of your things as gas phase atoms, then gas phase ions, and then you condense them into the solid. You add everything up, and then it's just an algebra equation, right? Basically, what happens is you'll always have all of the things except one, generally the lattice energy. One of the things we talked about in the video was the concept of lattice energy, and then how to and the factors that influence lattice energy. So if you recall, if I look at, say, these three compounds, and I say I want to rank these in order of increasing melting point. So one of the things about, just like ionization energy questions or atomic radius questions or anything like that, they're always going to be comparative questions. I don't expect you to know numbers off the top of your head. Obviously, I don't, but I expect you to be able to justify things or rank things. So if I ask you, for example, I ask you to rank these in order of increasing melting point. When it comes to ionic compounds, we can use lattice energy as a way to gauge melting point, because basically the lattice energy, the strength of the lattice energy dictates how much energy it will take to separate the particles. And so that's how much energy or how much heat energy will be required to melt the substance. So my first question is then, what equation governs lattice energy? Coulomb's law. So just like a lot of other things in this class, Coulomb's law says that energy of attraction between charged particles is proportional to product of the charges divided by the square of the radius of the internuclear distance, right? So here we go. So that means the way we're going to judge these is by looking at their charges and looking at their sizes. Now, so if we look at, say, lithium iodide, the product of the charges, so we have lithium plus and I minus. We have calcium oxide, right? That's going to be calcium 2 plus and oxygen 2 minus. And then rubidium iodide is RBI. So that's RB plus and I minus. So in general, the product of the charges is the more significant factor. So that means that calcium oxide has the largest product of the charges, right? So for this one here, right, here Q1 times Q2 is equal to -4. So that's the biggest. So this one will probably be the highest lattice energy, most likely. Also, then in the next one, both of lithium iodide and rubidium iodide, the product of the charges is 1 or -1. But so then it becomes a matter of judging the size. And so remember, the smaller the internuclear distance, the closer together those particles are, the stronger the attraction is going to be. So rubidium is significantly bigger than lithium. It's down at the bottom of that list. So if we had to rank them, I'm going to say rubidium iodide will have the least exothermic lattice energy. It'll have the weakest lattice energy, so it'll have the lowest melting point, followed by lithium iodide, and then rubidium iodide. Really, that's it. That's the kind of question you'll probably get. That was brought up in the class was this idea of the Born-Haber cycle, and so remember, the Born-Haber cycle it's not a real thing. It's a model of which gives us a mathematical way of doing things like calculating quantities that are hard to measure. Like we said, lattice energy is very difficult to measure directly. It's often easier for us to be able to measure some of the other properties and then go through the Born-Haber cycle to fill in the blanks. The Born-Haber cycle, I did an example for sodium chloride, I guess, right? So let's look at a different one. Yeah, all right. So let's look at silver chloride. So the goal here is to ultimately find the lattice energy, right? And so what we're going to do is we always look at this in terms of the overall reaction being Ag solid plus a half Cl gas, Cl2 gas goes to AgCl solid. Remember, this reaction here is the reaction of formation of the compound, and the enthalpy for that is called the enthalpy of formation. Formation or enthalpy of formation refers to a very specific thing. Okay, it refers to the formation of a compound from its elements. There are other ways to make silver chloride, but if we're doing this and we're talking about Born-Haber cycles and enthalpies of formation, it's referring very specifically to the formation of the compound from its elements. Now, the key with the Born-Haber cycle is that, all right, so the key is that if we can figure out a bunch of steps that sort of simpler steps that add up to the overall steps, then that's how we're going to do this, because we can figure out how to, because a lot of the quantities, the ionization energies, all of that, those are known. The lattice energy usually is the one that isn't. I mean, look, the reality is nowadays, lattice energies for most common ionic compounds have been published somewhere. This is sort of the process that was used in order to model them. And I think it's instructive for us to go through this and see how this works. So remember, the model that we use for Born-Haber cycles is that we look at our starting reactants, and then we have to vaporize it. We have to get everything into the gas phase. Then we have to make sure we have gas phase atoms. Then we transfer our electrons and then condense everything into the solid state. So the first thing that we're going to do is make sure we get everything into the gas phase. So for example, so if we start with silver solid, right? And we're going to go silver solid, and we want to turn it into silver gas. Okay. Now, I want you to remember, again, this is just a model that we use. This isn't exactly how it happens in terms of what actually happens. We don't need to worry so much about this because this is just a model, but it works. And this is sublimation, right? Going from the solid to the gas is called sublimation. So I'm going to call this delta H of sublimation. Now, sometimes, again, I'm sure I pointed this out before, but we say some examples will just number the steps in the reaction. I prefer to be descriptive. And again, that's just my preference, but it helps me organize my thoughts. So I've got gas phase silver. Chlorine is already a gas, so I don't need to get it into the gas phase, but I do need to get it as an individual atom. And so that's going to give me one chlorine gas, and that's the bond dissociation energy. So I call that the BDE. All right. Just a reminder, right? When we're doing thermodynamics, fractions are acceptable in balanced equations, but only when we're doing thermodynamics. Anytime you're looking at a balanced equation, fractions are not acceptable unless we're doing energy calculations. So now that I've got my gas phase atoms, what do I have to do? Here, chlorine is a covalent compound. Well, it's not a compound, but it's a covalent element. And we need to break apart the Cl-Cl bond in order to get just one chlorine atom. And that energy is known as the bond dissociation energy, long to right. So I write the enthalpy of bond dissociation energy, but I write enthalpy of BDE, right? So remember, delta H is enthalpy. It's the heat energy required for something. The next thing that we have to do is transfer electron. So silver is going to lose electrons, right? It's going to be oxidized, and then chlorine will accept it. transferring electrons. So silver, again, the order here doesn't really matter, but for me, it makes more sense if something gives up electrons first and then something takes it. Doesn't really matter. But so I'm going to say, oh, that's terrible. So silver gas becomes silver ion in the gas phase, right? And that is the first ionization energy of silver. Then what happens is chlorine gas is going to accept, oh, you know what? I made a mistake. All right. This equation here is not complete because I left out the electron. And then chlorine gas is going to accept that electron and give me Cl minus. And that corresponds to the first electron affinity of chlorine. Right? Again, how you label it doesn't really matter. Okay, as long as I mean, frankly, it would be acceptable if you labeled the steps A, B, C, and D, or 1, 2, 3, and 4. I try to be descriptive. It's helpful for me. So now I've got my gas phase ions, and the last step is to condense those ions into the solid state, right? So I have, oh, no, again. Ag plus gas plus Cl minus gas goes to AgCl solid. And that is the lattice energy, which I usually call delta H lattice. So these are the steps. And remember the specific steps might be different, but the general steps are always the same, which is you want to get everything into the gas phase as gas phase atoms. So the silver, we get everything as gas phase atoms, transfer our electrons, and then condense into the solid state. And if we followed Hess's law, we could check and make sure everything cancels out, and it would give us, in fact, the initial reaction overall. So that's always a test that you can do for yourself. Before we move on, what I want to check, and before we bring numbers into this, actually, is we need to decide which steps are endothermic and which steps are exothermic. So sublimation, is that exothermic or endothermic? It's endothermic. Remember, endothermic means you have to add heat energy to something. So in fact, it makes sense going from a solid to a gas is something that is endothermic. What about bond dissociation? Breaking chemical bonds is always endothermic. So forming chemical bonds is exothermic, but breaking them is endothermic. What about ionization? So the first ionization energy. So removing electrons is always endothermic, no matter what. And what about the electron affinity, the first electron affinity of chlorine? First electron affinities for the nonmetals are exothermic. And then the lattice energy also is always exothermic, because if you think about it, we're bringing charged particles close together, so energy is released. Now I've got all these numbers, and we can try and figure out what the lattice energy of silver chloride is. So the enthalpy of formation of a reaction is actually, remember, the enthalpy of formation for a reaction is equal to the sum of the enthalpy for the steps. So all these steps here, becomes then just an algebra problem, right? It becomes an equation, and you have to just decide which one is your unknown. If we look at this one, the enthalpy of formation is equal to the delta H of sublimation for the silver then it's equal to the bond dissociation for energy for chlorine. But we have to be careful because the bond dissociation energy, that term actually would refer to not half the reaction. This term here would actually refer to Cl2 going to 2Cl. So we actually need half of the bond dissociation energy. So it's 1/2 delta H of the BDE plus the first ionization energy plus the first electron affinity plus the lattice energy. And we have all of the terms except we're missing one, right? So we have minus 127 equal to 289 plus 1/2 of 242 plus 789 plus minus 364 plus the lattice energy. Right, so now it's just a rearrangement. We can just collect all our terms. 289 plus 121 plus 789 minus 364, 835. So now we get minus 127 is equal to 835 plus the lattice energy. So subtract from both sides. So this becomes, right, so this is minus 127 minus 835 equals the lattice energy. And so this becomes, what is it, minus 962 kilojoules per mole. And that's the lattice energy. So that's how you solve Born-Haber problems.